Assalamu alaikum everyone. So in the previous session, as we dwelled in the details of basics of linear algebra, so in there we discussed what vectors are, how to represent these vectors, what are Cartesian systems, and then how to represent these lines and planes. A lot of stuff that we have covered. Now we'll take from there, and then we'll move on to the different concepts and other concepts of linear algebra. So the revision I want to do here is so that get to know what we are talking about. Again, I'll just say that vectors, they basically are just bunch of numbers as we have these lists. So in Python we have this list 1 comma 2 comma 3 like this, so we can treat it as a vector. So we have developed in the deeper details of these, but uh, for the matter of today, you just remember that vectors are lists if somebody has missed the previous lectures. So here we can represent lectures. Let's suppose anything can be represented basically by a vector. Suppose we have a house, and in this house, if we want to represent it as a vector, so maybe you are selling this house, you are having this house on sale. So what you can do is you can maybe have two values in which the first value will represent square footage of the house and the other value will represent the cost of the house. Let's suppose if the square footage of the house is 2000 square feet, and let's suppose the cost is 2 lakh rupees or something like this. So this basically becomes a vector. So in mathematics and computer science, these numbers basically have some representation. In CS, like I gave you a concrete example of house. So any of these two numbers basically represents a house. So in the similar fashion, what if I wrote like this? I can write 2 lakhs first, and then I can write square footage next. So clearly these two vectors are not equal. So these two are not equal. So why are not they not equal? Because the order matters here. So we can say in vectors order matters. Okay, so this is the revision I want you to take, that vectors are just a list of numbers that we'll think of these vectors are just list of numbers. Then these vectors, if we have a vector like 1 and 2, and if we write a vector like 2 comma 1, these are not equal because the first number represents something else and the second number represents something else. In the mathematical scenario, we saw that the first number is, if it's a 2D vector and we draw it on a 2D plane, so this will be the x component. So in the second vector basically is the y component. Okay, so this is just in the 2D plane which we saw in which we saw previously in the previous session. So now we'll go into the basic details of the things that I wanted to show you. The first concept that today we'll take that as vector addition. Now we'll have the focus as much as possible so that you understand these topics, because these are building blocks. Then we'll move on to the more complex concepts. So what basically is a vector addition? So let's suppose again I'll make two vectors. That's why I have just pasted this over here. So let's suppose I'll make two vectors. Let's first mark this is value 1, this is value 2, value 3, and value 4. This is also 1, 2, 3, and 4. Let's suppose we have a vector like this. So if we have a vector which is like this, I'll just make it a little bit larger size so that it's visible. Let's suppose this is a vector. So this vector, clearly it is 1 comma 3 because its x component is 1 and y component is 3. Let's suppose we have some other vector like this. Clearly you can see that this vector is 5 comma 2. So the first vector that I have written here, so this vector, it is 1 comma 3 because its first component is 1 and the second component, y component, is 3. This vector over here, this basically is 5 comma 2. Okay, so what I mean by addition of vectors, so as you know, in the previous session we discussed the how to basically sort of think about these vectors. So if you think about this 1 3, it basically means take a step 1 from here along the x-axis, then take these 3 steps along the y-axis. So that means you will reach this point if you take these 2 steps. So in a similar fashion, if you see about for these vectors, for this red 5 comma 2 vector, so you basically are telling me that just take this much of distance, that is 5 units distance along the x-axis, and then 2 units of distance along the y-axis. That's how you will reach the vector, this red vector. So now what if I want to see the combination of the effect? If I want to see the combinedly, if I somehow combine these effects, let's suppose you are going on some place, you are going here, first you will go in this direction, then maybe you'll go in this direction, maybe then you'll do something, and I want to see the combined effect, the resultant effect of these two vectors. So what I can do is, so I can first walk along here on this, for this yellow vector. What I'm doing is I am walking 1 unit on the x-axis, then I am walking 2 units or 3 units on the y-axis, then again I have to walk these many units, like for the 5 units along the, these many units along the y-axis, and then x-axis, then I have to walk again down the y-axis to reach here. Okay, for example, I'm just showing it if I want to reach the resultant. So how the resultant basically is, so just like deleting the things so that you can clearly see it. Okay, so what I want to see basically is I want to see what is the combination of these two vectors. So here what I will do is I will first see how far how to take some steps so that I can cover this. So this is the first step that I'll take. Then I'll take again this one step, and then I'll take the 5 steps, because the x component of this is 5, so I'll take some other steps, so it will go right here out of the graph basically. Then I'll take the steps, one step, 3 steps basically over here. Okay, 3 steps that the x-axis are. So because this yellow vector, the y component is 3, then for this red vector y component is 2, then we'll take 2 y components over here. So we'll reach somewhere around here. Okay, so what I mean by that is, so basically all of this blue shows the net effect, the resultant effect of the two vectors. It shows the resultant effect of two vectors. So if we combinedly took these steps, so first what we did is we have to take one step for this yellow vector, one step along the x-axis, and again 3 steps along the y-axis for the yellow vector. And for the red vector, we had 5 steps along the x-axis and 2 steps along the y-axis. So combinedly, if we want a combination vector, let's call this vector as resultant vector. This vector, call it resultant vector. So it basically means that add the two components here, 5 plus 1, 6. So you have to walk 6 units. That's what I did. I walked basically 6 units along the x-axis. Then what I did is along the y-axis, I'll walk 2 plus 3, that is 5 steps. So along y-axis, I'll walk the 5 steps basically. So I'll reach this point out of the graph basically. So we can draw a graph which I call a resultant graph like this. So it will be over here. So this is the resultant graph. Maybe drawing it again so that it's clearly visible. So this is the resultant graph. This vector is the resultant vector, this vector. Or we call this vector as the addition of these vectors. Let's suppose this vector was v1 and this vector was v2. This vector will be v1 plus v2. That's what I mean by the addition of vectors. So you saw that we add the vectors component wise. Addition of vectors. So in that, if we had a vector v1, okay, then we had a vector v2. So what's the resultant of these vectors? Resultant is v1 plus v2. This is the resultant of the vector. So how we add these vectors? Component wise. Let's suppose v1 vector, it basically had, let's suppose x1 comma x2 till xn components, and then we had this v2 vector, its components were b1 b2 till bn. So what will be this v1 plus v2? It will be x1 plus b1, x2 plus b2, and so on till xn plus bn. So if I want to show it again geometrically, I have showed you here. So this is the first vector v1, this is the second vector v2. So in this, what we did is, what is the combination, the effect? So vector addition basically is the process of combining two vectors, which creates a new vector. Okay, so this is the definition. If you want to write the definition basically is how we combine these vectors. So this is the process of combination of these vectors. Okay, let's now see. This basically is the mathematical way by using the numbers. If we have to use geometrical ways, okay, so how to add these vectors, to arrive these add the vectors. So what I'll do is I'll again mark some vectors. So let's suppose here this is a vector. Let's make it good. This is a vector, and then we have a vector like this as well. Let's suppose this is a vector, this and the vector. So if you just mark these lines, this is 1, this is 2, and this is 3, this is 1, and this is 2. The origin is 0 0. So this vector basically represents this vector. It represents 3 comma 1. So this vector over here represents 1 comma 2. So these are the values of these vectors. So how to basically now compute the resultant graphically? So there are two methods. One is called as tip tail method. So one method, there are two methods. So in order to show the graphic list, now you know that mathematically you can just take these vectors and then you can add them component wise. If you want to see it graphically, so I told you that there are two methods. The first method is called as tip to tail method. Why am I going into these details? Because I want to internalize these concepts so that we visually see these things. So what is the tip to tail concept basically means? You can move this vector. For example, if we have to add the vector, let's call this vector v1, let's call this vector v2. So if you want to compute v1 plus v2, so what you can do is, this is the tip, this is the tail, basically this vector origin, and the tip means basically here, this is the origin, this is the vector, the arrow where it points. So what I can do is I can just take the vector and take this vector, sorry, so I think I deleted something. I can just take this vector, then I can move it around. I can basically move this vector around, this vector, this vector I can move it around. So the net effect basically will be, it will be a vector like this, which will be quite here if I move this vector from here to here. So the tail of the vector basically falls in the tip of other vector. So what I have done here is, if you again see, I have just brought this vector over here, this vector I have shifted over it here. Okay, now what I'll do is, I'll just go from the tip of this vector to the tail of this vector. So this vector which I have written in the dotted lines is the resultant vector. This is the resultant vector basically. So again, if you see what are the coordinates of this point now, so this point's coordinates are 4. So you can see this point's coordinates are 4, and then dropping a perpendicular 3. So 4 comma 3 is the resultant of this, if you see it graphically. So 4 comma 3 is the vector. So if you again mathematically try to see it, so we had vectors 1 2, then it was added with 3 comma 1. So this basically is 4 comma 3 if you see it component wise. So graphically you also saw that we just took this vector v2, this vector over here, then we shifted over here because it's tail, and it was taken, this tip was taken and this tail was taken, it was just plotted on the tip of the other vector in order to compute the addition. This is called as the tip to tail method if you want to see it graphically. So again, there is another method called as parallelogram method. There is a method called as parallelogram method. This is when you have vectors in the visual format, but mathematically how do you add these vectors? Just add them component wise. So similarly, taking, if we had again two vectors like this, again we had a vector like this, making a thicker line, having a vector like this, then a vector like this. So now what is this parallelogram method? So this parallelogram method says basically just complete the parallelogram. So how can we complete this parallelogram? Just draw a line parallel to this. So this line, there should be a line parallel like this. Okay, then draw a line parallel to this. It should be like this. Okay, so now whatever the diagonal of this parallelogram is, the diagonal is this much. So this is the resultant vector. Okay, so both of these results, both of these methods, they basically give the same result, that we got the resultant vector. So what we saw is, we saw three methods. First, the mathematical one, in which three methods are. The first method is that you saw the method in which we add components. Add components. Then two graphical methods were, first you used uh, tip to tail method, and the other method that you use was parallelogram method. Okay, I hope the concept of this vector addition is clear. So basically vector addition means, if we have a bunch of vectors, for example a vector like this, a vector like this, and a vector like this, and we want to add these vectors together, so we want to find a vector which is equivalent to what these vectors were doing. So we want to find just one vector, so which basically produce the effect of what these vectors were producing individually. So and by combining that effect, and we'll just plot one vector so that it shows the effect of all of these vectors together. So is the concept of addition of vectors clear? Is it
Yes,
clear?
sir.
Nice. Okay, so there are different properties of the addition. So what I can say is, I can write properties of addition. Properties of vector addition. The first property is, it is commutative. Commutative means if you are having two vectors v1 and v2, irrespective of what is the order in which you compute, you can compute v1 plus v2 or v2 plus v1. So this basically is commutative. So this is called the property of commutativity. So vector addition is commutative. Okay, this is basically really easy. Howsoever you do, and if this is a vector v1 and this is a vector v2, so you can add v1 because addition is commutative and we are adding the individual components here. Okay, so that's why irrespective of whether you add v2 plus v1 or v1 plus v2, it will the same answer. That's what I'm saying, addition is commutative. It's also associative. Okay, associative means if we have three vectors v1, v2 and v3, so we can compute the vector addition like this. So let's combine first v1 plus v2, then add that v3 to the resultant that we got out of v2. Or we can do like this, we can first add vectors v2 plus v3, then add v1 to it. So this basically will give you the same result. So this property is called as associativity. So vector addition is also associative. Okay, and there is an inverse of there are a lot of properties like additive, identity, inverse and thing, but I want you to remember these two things, and these two properties will be really important when we these vector additions. I hope that with properties then we have additive, identity, inverse. I don't want to go in the details of those, and you can find a lot of mathematical books in there. But here I want to show you the intuition of what a vector addition means. Again, to reiterate, vector addition basically means if we have a bunch of vectors and they are producing a certain effect, and a vector which is called a resultant or the sum of all these vectors is basically a vector which is producing the same effect which the vectors were producing in the combined form. That I have given example. If you have three vectors and they are producing some effect, and I can replace all of these three vectors by just one vector, and this one vector is producing the same effect which these three vectors were producing. This is the concept of vector addition. We saw some graphical methods how to plot these things and how to add these vectors graphically, and we saw how to add these vectors mathematically by just adding the components of these vectors. I hope the concept of vector addition is clear. Now I'll move to the other property. Maybe I'll just show it in the code window so that you also see, because it's similar what I have shown on the paper. So here this is what's vector addition. So we have a vector v, we have a vector w, red vectors and blue vectors. Okay, so then this vector, the middle vector which is green vector, is the resultant. You can get it by using the addition law or by using the graphical methods in which we have parallelogram law, and we have that tip to tail method, these two methods, and you can get this green vector. So this is the additional vector, a resultant vector basically. Okay, now we'll go to what is called as scalars. The first thing we saw addition of two vectors, then we'll saw multiplication of a vector by scalar. So we'll see scalar multiplication, in short, scalar multiplication. What is the scalar? These concepts are really easy, but to get the intuition behind it, it's really important. Okay, so basically this means if we have a vector, let's suppose x vector and its components are x1 and x2. Let's suppose this is our vector. Okay, so what if I have a scalar? Scalar basically means I have a value, let's suppose 2, or some scalar value a. So this basically will produce an effect. You multiply a multiplied by the x1 component, and you will do a multiplied by the x2 component. So this is what we call as a scaled vector. Scaled vector. So scaled basically means you are some sort of scaling things either up or down. Scale up, scale down means making a vector bigger or smaller. So scaling basically means you are doing something with the vector. So here, as you saw, that this is the mathematically how we define this scalar multiplication, or multiplication of a vector by a scalar. So this is called a scalar. So because what it does scaling. It either decrease or increase the vector. So how to do it? Just component wise multiply these things. Okay. So this is how to basically. Now I want to show you the geometric intuition, what basically this means. So again, going to the graphical methods to show you what the scaling basically means. Let's suppose we have a vector. We'll just plot one. This is 1, 2, and 3. 1, 2, 3, 4. Let's suppose we have a vector 2, 2. This is our vector 2, 2. Okay, so this is our vector. So I can write mathematically this as 2, 2, 2, 2. This is the vector that we are speaking about. So what if I just multiply it by, let's suppose, 2? So this vector mathematically will become 4, 4. So the effect will be, I'll get a vector new. Let's make that green. So this is 4 and 4. So vector should arrive at here. That resultant, the vector scaled vector should be here. This its values are 4, 4. So this is the scaled version of the vector, initial vector that we have. Okay, so this vector we call it a scaled vector. So it basically multiplies all the components. Okay, so you can do the scaling in the negative side as well. Okay, if you do for example by -2, this vector will reach here. If you do it by scaling by -2, so this will basically reach somewhere around here, 4, 4, something like this. Okay, So this is 1 2 3 and 4, 1 2 3 and 4, huh? So this vector, if you have this 2 multiplied minus 2 multiplied by 2 cut 2, so this will be negative 4 4. Okay, so you can just scale the vectors up. So if you have a vector like this, some vector like this, so you can scale the vector by multiplying in the same direction. Okay, so anything you can get out of this vector. So this is the vector that we're talking about, this yellow vector. This is called as a multiplication by the scalar. So this basically does the job of scaling. If you see it, is the concept of multiplication by scalar really clear? So these concepts look really easy, but when we sort of merge these concepts with other things, so they become complex. So that's why I am showing these things in detail, and I know that these concepts are really easy. Okay, so this is the concept what I to call this as multiplication by a scalar. Let's now see again these standard 2 bases, and I can represent these vectors in some other format so that I can go ahead with the topic. So again, if this is a vector, we had this vector. So this vector basically represents 1 2 1 2. So this vector is 2 comma 2. This is the vector that I represent here. So we have something called as standard bases. Standard bases. So we'll talk about bases later. We'll talk about in depth what bases are, but know that there are something called as standard bases. So that is, we have a vector I hat and a vector j hat. We have a vector I hat whose value along the x-axis is 1 and y along the y-axis it's 0. Okay, and then we have a vector j hat. Okay, its component along x-axis is 0 and its component along the y-axis is 1. So these two are called the standard bases. So we can represent any vector in these standard basis format. Let's suppose we have a vector 2 comma 2 or 2 comma 3, let's suppose. Okay, this basically can be written like this. So we can write 2 multiplied by 1 comma 0, as we saw just scalar multiplication, plus 3 multiplied by 0 comma 1. Okay, so basically we'll get this vector back. So we'll get this vector back. So if you now see that I can write this 2 I cap or I hat plus 3 j cap. This is how I represent vectors component wise. So remember that these two are called the standard bases of the vector. We'll develop in the detail what bases are. So I promise you that, but just remember that we can represent any component in these standard bases. As we represent this 2 comma 3, we just expand it out, 2 multiplied by the I cap and 3 multiplied by j cap, if you see. Okay, so these are the unit vectors. Again, there is a concept what's called as unit vector. So unit vector has a direction and its magnitude is 0. Its magnitude is, sorry, not 0, its magnitude is 1 unit. So if you have a vector v, so how to get a unit vector basically means just have this vector v and divide it by the norm of v, basically the magnitude of v, so you will get the unit vector. Okay, I have told you how to compute this norm or how to compute this. This is basically summation of xi, I goes from 1 to n. Okay, so this is how you compute this and you square these things up. This is how you compute the norm. So this is what is the unit vector. So these two are the unit vectors and they are called as standard unit basis of a 2D plane. This is our 2D plane. I hope that the concept of standard basis is clear, because we want to represent every vector in this format, 2i I cap 3j cap. Okay, so we'll see the details of the basis in the subsequent sections, but here I want you to know that there are two vectors which are called standard basis for the 2D plane. In a similar fashion, the standard basis for the 3D plane, in which we have x, y and z axis, are I cap, comma j cap and k cap. So they are represented like this: 1 0 0, 1 0 1, 1 0, sorry, 0 1 0 and 0 0 1. Okay, then if for let's suppose we have nd plane, so in that the basis will be, so 1 then all zeros, then at the second place we'll have 1 all zeros. Okay, and so on, the last will be all zeros and at the end 1. So if we have what we call as nd vector space, okay, here this is the 2D vector space or the 2D plane that way, this is called as 2D real vector space. Okay, and then here this is 3D 3D vector space, and this is nd vector space, if you see this. So in all these vector spaces or all these planes, we have the standard basis. Okay, so how is the ith component? And we can say, let's suppose we have x1 x2 xi till xn are the axes of these planes. So how does this ith look? So ith component or ith standard component basis looks like all zeros. At the ith value we should have 1, and rest are followed by zeros again. Okay, so this is how what I mean by the standard basis. Is the concept of standard basis clear? Is it clear?
Yes, sir.
Nice. So now we'll go, if you have all these details, now if you have sort of understood these vector addition, then skip multiplication by scale, then the standard basis, now we'll see what algebra is there for, what this linear algebra is there for. That's a fundamental problem it does. So I'll write the fundamental problem of linear algebra. What it solves basically. So this is the problems that it usually solves. So what it solves, it, if we have n equations, basically these equations should be linear. That's why it's called linear algebra. So if we have n linear equations and there are n unknowns, okay, so we can find the solution to these equations. So basically the fundamental problem is finding the solution for the equations which have n unknowns, and there are n equations, and there is a must that equation should be linear. What's the meaning of linear equations? That for all x's there should be there it should be raised to power maximum 1. So it should be like this: 2x plus 3 is equal 4. For this is also a linear equation. Okay, so if we have a square in this variable term, so this is a quadratic equation. So I hope that you know all of these concepts. Just to sort of brush up these things, this is called linear equation. If the power on the variables is at most 1, that's called a linear equation. So here we'll deal with these linear equations. So if you remember that I told you the equation of line is w naught plus w1 x1 plus w2 x2 is equal to 0. So this was the equation of the line, if you remember the previous lecture. So in short, we used to write it like y is equal to mx plus c. Okay, so you can get this equation that's written in yellow by rearranging the terms in the right equation. So this is the generic equation of the line. So this is one equation of the line. Okay, so now I can show you two pictures of these things. The first picture I'll call it as a row picture. A row picture. Okay, let's suppose we have two equations. Let's again write the equation of two lines, and then we'll see the row picture. Let's suppose I have an equation 2x minus y is equal to 0. Okay, so here if you see this equation, so m is equal to 2, and then we have c, this is equal to 0. So this basically can be rearranged like this. This is our first equation, 2x minus y is equal to 0. Okay, and then we have another equation, minus x plus 2y is equal to 3. As you know that this is an equation of line and this is an equation of line, so we can easily plot these two equations which are called as row, and I can take one row at a time. So 2x minus y is equal to 0. Let's solve this equation. Let's take x is equal to 1. So for this equation, I can write x is equal to 1. So what is the value of y then? So y will be minus 2. Y will be 2, sorry. So if you just solve the put 1 over here, so it will be 2, and then 2 minus y is equal to 0. Then y on the other side, y is equal to 2. So I can just plot these values. So I'll write 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. So this is the first point of the line, x1, y2, x1 and y2. This is the first point. Then I'll again put some value. Let's suppose I'll put a value x is equal to 0. Let's suppose x is equal to 0, y is also equal to 0. So this will be, this basically passes through the origin. If x is equal to 0, y is also equal to 0. If x is 0, y is also equal to 0. So this will be the second point of the line. So we have 2 points. 2 points are more than enough to just construct a line uniquely. So this is the line basically. So if I write, so just making it a little thicker. Not quite well. I just wanted to make the straight line. Anyways, so this is a straight line, let's suppose. So this is a straight line anyway. Maybe I can just use the tools. So how to put a straight line? Let's suppose this line is fair enough straight. Okay, so this is the one line which represents 2x minus y. So this is the line, this one, 2x minus y. So again we can draw a line, because you know this is the equation of line. Again, just plot it. Let's suppose x is equal to, if we put x is equal to 0, then y is equal to 2 by 3. Let's put x is equal to 1. So x is equal, let's suppose 1. So we have minus 1 plus 2y is equal to 3. So y is equal to 1. if you solve this equation. So y is equal to 1. So this is the first equation, 1 1. So this is the point. Okay, then if we want to put some other values, just cross check my, if I'm doing correctly, cross check these values. If x is equal, let's suppose 2. If I put 2, so this is minus 2. Then I have plus 2y is equal to 3. Then I have 5 by 3. uh, 5 by 3, basically I want an integer value. Let's not put 2. Let's put 3. So minus 3 plus 2y is equal to 3. So y is equal to, I think, 3. Y is equal to 3. Okay, so x is equal to 3 and y is also equal to 3. So this is the point, 3 comma 3. So this is the point. So now we have 2 points, and these 2 points are enough to sort of have a line. So we'll just draw a straight line. Now if you sort of see these lines intersect on some point, okay, you see these lines do intersect on the point. Maybe the calculations are here and there wrong, and but I want you to focus that here we have two lines which intersect, and this is called the solution of these equations. So these two equations, so this is an equation of line, this is an equation of line. Our job was to find the value of x and y so that these two equations are satisfied. So we can draw that graphically, which I call as a row picture. I took one row at a time. I took whole of this, okay, first row, and then I took the second equation, this. So I have plotted them. I saw what is the point at which they meet. So I call this the solution, which I wrote, solution of these two equations, or solution of these two lines. To show you this graphically so that the graphs are neat and clean, I'll like to go over the coding window because I plotted this somewhere. Okay. So these are the two lines if you see it. Maybe I have made the graphs wrong, but here the graphs are quite accurate. So the solution to the equation is basically 1 comma 2. So if you need these two lines basically meet at 1 comma 2, that I'll write here. So the solution to these equations is 1 comma 2. So that is the fundamental problem which algebra solves. It basically, if it is given a bunch of equations and bunch of unknowns, so we want to find the unknowns. So that's what it does. The first picture that we saw is called as the row picture. So just focus on this and see that solution here, they intersect on 1 and 2. This is the point they intersect on. The solution to these two equations is 1 comma 2. Okay, so this is the solution to these equations. 1 comma 2 is the solution to the equation, and we solved it by using what's called as the row picture, and we solved it. This is the solution. So then I'd like to go what's called as a column picture. Okay, again we have the two lines like this. So this is the graph. So we have these equations. So we have 2x minus y, and then we have minus x plus 2y is equal to 3. So I can write this equation like this. So I can write 2 minus 1. If you see it right here, 2 and this minus 1, this 2 and this minus 1. This is what I wrote, 2 and minus 1. And maybe I can multiply them together with x plus. Okay, then I'll take a y and minus 1 comma 2. So here I have minus 1 comma 2, and I'll multiply it by y. This is equal to 0 comma 3. Okay, so basically my job here is to find this x and this y so that this equation is satisfied. Now you know what is scalar multiply. That's why I told you, like, focus on scalar multiply. Now you know that this is 2x plus minus y is equal to 0, minus x plus 2y is equal to 3. Now you know that this is a vector basically, so I can plot this vector 2 comma minus 1. So I'll just write 1 2 3 4 and 5, minus 1 minus 2 minus 3 and so on. So I want to plot this 2 minus 1. So 2 minus 1 is here, so 2 is here, and minus 1 basically is here. So this is the vector. Okay, so this is the vector, this is this vector, and then I have vector minus 1 comma 2. I basically rearranged the equations. I had equations 2x minus y is equal to 0. Then I had other equation minus x plus 2y is equal to 3. So I basically rearranged these equations like this in the form of vectors. So now I am plotting these vectors. Why is column picture? Because I am taking sort of columns of these. Initially it was called a row pictures because I was taking row of these things. So I was taking this and this. So now what I am doing is I am taking columns at a time. So now I have 2 comma minus 1 plotted over here. Then I have minus 1 comma 2. So minus 1 is over here. Then I have 2, basically minus 1 is here. Then 2 is 1 and 2. So this is the other vector that we have. So I'll plot this vector like this. So these are the two vectors. So this here is 2 minus 1, and this vector over here is minus 1 2. So I want to reach vector 0 comma 3. So I want to reach vector 0 comma 3 over here, I think. Yes. So this is 1 2 and 3. I basically want to reach this vector. So I'm saying, can I use some of these vectors? Can I use these vectors somehow so that I can reach to this point? Okay. So maybe I can do one thing. What I can do is, so I have to reach the vector 0 3. So this is the vector I have to reach by using the vectors these 2 comma 1 and 1 comma 2. And what I can do is, I can take one of this vector, maybe one of this vector, and I can take two of these vectors. Let's suppose I can take two of these vectors, 1 till here and 2 till here. So what I did is, I took one of this vector. So I took one of this vector, okay, and then two of this vector, and that makes me the solution. That's the value I'll put here. I took one of this vector, okay, and then I took two of these vectors to reach this point 0 comma 3. That's the reason I'm saying the solution is 1 2. X is equal to 1 and y is equal to 2, because what I'm doing is, I'm taking one of this vector, one of the red vector, and then I'm taking two of this yellow vector to reach the resultant vector 0 comma 3. So in both the things, if you see this row picture, we just constructed a line and found the common point. That was the solution. So in here we saw how to basically combine these vectors. What proportion should we combine these two vectors into, so that we reach this resultant point, this point basically. And we got the solution, x is equal to 1, y is equal to 2 in both the cases. So is the row picture and column picture clear? Maybe this was a little bit engaging, but just remember that these are the two pictures how we can solve these. Can I move ahead? How many people are convinced that we can these row pictures and column pictures can be used to solve these linear equations?
सर कॉलम पिक्चर रिपीट करना.
Okay. So what I did in the column picture, I had these two equations. If you see this, I had these two equations. So what I did is, I took the coefficient. This is called as coefficients, 2 comma minus 1. So this is the coefficient. I wrote it like this. Then I had the coefficient minus 1 and 2. I wrote it like this, minus 1 2. Okay. Then I just put the scalar multipliers in x and y. So if you expand this equation, if you expand this equation, so what will happen is, so this equation will be basically this. If you multiply this x with 2, and you will get 2x, and then you list this is the 2x, and then minus 1 comma y, this is minus y, is equal to 0, is equal to this. So this is the format in which we wrote these equations together. If you know now, these things are vectors, these two things are the vectors, and this is again the resultant vector. So what I want is, I want to combine these two vectors somehow, this vector and this vector. I want to combine this, and somehow I want to put proportions in somehow, so that I get this vector. So what I did is, I plotted this vector 2 comma minus 1. So this is the vector 2 comma minus 1. If you see, this is the vector, that red vector is the vector that I plotted here. So this vector over here, so this is the vector 2 comma minus 1, which I had here. Then I had vector 1 comma minus 2. So this is the vector 1 comma minus 2, if you see this vector. Okay. So now I also plotted 0 comma 3. This is the vector that I want to reach. Now what I'm saying is, I want to use combination of these vectors, this vector and this vector, yellow vector and a red vector. I want to use the combination of these two vectors so as to reach this vector. Okay, in what proportion should I sort of add these vectors in order to reach this? So what I did is, I just used one of this vector. So 1 basically means 2 comma 1. I used the quantity 1 of this vector. Then I added this vector twice. Okay, so this is the first, so this is one vector, and then again putting it the same vector back. So this is basically scaled version of this vector. So if I scale this vector 2 times, so this vector will become bigger. I'll put this vector over here. So this is basically the 2 vector. Let's call this vector as v1, and let's call this vector as v2. I used one quantity of v1 and 2 of v2 and add them together so as to reach this vector, which call as 0 3. Let's call this vector as v3. So I wrote basically 1 times v1 plus 2 times v2 is equal to v3. So I used 1 of v1 and 2 of v2s so as to reach this v3 vector. So this is what I call as column picture. And the solution we arrived, this is the solution. These coefficients are the solution, 1 and 2. So this is the solution to these equations. Is the column picture clear now?
Yes, sir.
Nice. This is really important, because why I'm giving you these intuitions to solve these equations, because you will be doing machine learning and a lot of stuff with these, and all the things that you see on the screen, graphics and things, these all things are done by linear algebra. So that's why you must have all these things really ingrained in your head. That's the reason I'm sort of spending more time in order to brush up your basics and make them really stronger, and you have the intuition as well. Nice. So we now solve these equations. Again, I would like to show you it in the code much clearly. These are the two equations which you have. So here this is a 0.11, and now how is this column picture? Not like this. So this is the column picture. So we had to reach this vector. Let's suppose we had to reach this vector. So I used one of these and two of these. Okay. So this is how I reached over here. And I think this 0,3 it was not accurate. 0,3 should have been like this. Okay. There's a little bit mistake the painting that the drawing basically that I made. So this 0,3 should have been over here. It should have been over here because 0 was the axis value and 3 was over. This should be the vector. That's the reason I have kept these figures so that when you want to see this and they are clearly mentioned there. So I have taken one of this vector and two of these vectors, one and two of these vectors. That's what I showed you on the code. So this is the vector that we want to reach, the green vector, and I have to use some combination of this blue and red vector. So I used one red vector and two of these blue vectors. Basically I scaled this up so that I can reach this blue vector. So that's the column picture over here. Can I move ahead with the next concept? Is it clear how to solve these equations? Is it clear?
Yes, sir.
Nice. We can do the same in 3D. So if you want to do the similar thing in 3D, so you know that in 3D the equation basically of line becomes a plane. So you saw the equation of plane is w0 plus w1 x1 plus w2 x2 plus w3 x3 is equal to 0, and you know this is an equation of plane. Now here we have basically three unknowns and we have three equations. So in the previous case this was a linear equation in which we had two unknowns and two equations. We had equation 1 and equation 2. The unknowns were x and y. So here we have these unknowns. W1 is an unknown, W2 is an unknown, and W3 is an unknown. So we must have three equations and three unknowns in order to solve this. So I again like to give you some more things. For example, let's suppose in 2D, if I have a line like this and like this. So this is, let's suppose, line 1 and line 2. So line 1 basically means equation 1. So in this case, there will be a unique solution. So you might have heard these two equations have unique solutions. That basically means these two lines intersect at only one point. There can be two lines which can be like this. One line is like this and there is a parallel line. So in this case, there will be no solution because these two lines do not meet at any place. Okay, and then there can be two lines which can be on top of each other like this. So we have a plane in which one equation is like this and the other is on top of that. So here we have infinite many solutions. Infinity many solutions. Now you know your intuition is clear because an equation which is basically in 2D plane basically represents a line. So that we have seen. So if two lines intersect at a single point, then we call those two equations have unique solution. So if the two equations have they're parallel and they don't meet anywhere, then we call them it has no solutions. So if these two lines they basically are on top of each other, we call them these equations have infinite many solutions. I hope this is clear, and you can move up to this 3D, ND, and ND maybe wheresoever dimensions you want. That's the beauty of algebra. So you just visualize things to 2D and 3D, then you can move ahead the things onto 4D, ND, which you can't visualize even. Okay, similar thing can be done with the what I was talking about 3D. So you can just have 3D. In 3D we have these planes. If we have 1, 2 and 3 axes, so we'll have one plane like this. Let's suppose we'll have one plane like this. Then we'll have some other plane like this. So two planes will basically meet at a line. So only three planes will basically meet at a point. Okay, so as we had these two lines, they'll meet at a point. So if you have a plane and they cross each other, so they'll cross each other at a line. So there will be a line. So if you have three planes, they'll meet at a point, and we want to find these meeting point. So this point we want to find. That's the solution to these equations. Okay, for that I've also given you a demonstration. Let me just show it clearly on the screen so it becomes good. So where is that? It's here. So I have just mentioned, you know how to draw a plane because we have discussed the extension in the previous session how to draw this plane. So the equation of plane you know, and from the equation I have just sort of drawn three surfaces, and you saw these are the three planes that we are having here. So these three planes basically meet at one point and we want to find that point. Maybe here it's very difficult to visualize this point, but algebra will take care of that job and it will just solve the equation and see the right combination with these planes can be set into, and then we can get basically the point where they intersect. That will be called the solution of these equations. What we are doing is we are basically seeing what is the fundamental problem that the algebra is solving. The algebra is basically solving the fundamental problem of finding a solution to the n equations which have n unknowns. So in order to solve anything, if you have n equations, let's suppose unknowns are n plus 1. So it's not, we can't be solving that. It's basically saying that you have, for example, let's suppose two equations and you have three unknowns, so you cannot find it because you don't know the picture how it will form. Okay, in order to solve anything, you must have n unknowns and you must have n equations corresponding to that. And we'll see the sophisticated method how to find these points by using the what's called elimination methods, Gauss-Jordan methods, and we'll see that. But I just wanted to give you intuition what are we up to and what are we going to find in these things. Okay, if this is clear, I can move ahead to the next topic. Is it clear? Nice. I want to have a thumbs up from everybody because I switched the screen. I want to see if everybody is able to understand. Subina, are you there? Nice. Now we'll see what is the meaning of linear combination. I want to go to the linear combination of vectors. Linear combination. I've already discussed that, but I just want to show you how to basically define a formula and what is the meaning of the linear combination. So if I have this 2D plane, okay, if I have this 2D plane, which I showed you in the previous case, so this is the 2D plane. Oh, I think I cannot paste it. Huh, I can. So this is the 2D plane if I have. I told you if I have any vector like this, okay, this vector is basically the value of this vector is 3 comma 3, I guess. So 3 comma 3 is the value of this vector. So I told you I can write it like this. So I can write this 3 comma 3 as 3 multiplied by 1 comma 0 plus 3 multiplied by 0 comma 1. So basically 3 I cap plus 3 j cap. Okay, so this is what I mean by the linear combination. So I'm combining these two vectors linearly. Okay, I'm combining some vectors. Let's call this vector as I cap and j cap. I'm combining the I cap and j cap linearly in some combination to get this vector 3 comma 3, this vector. Okay, let's suppose I do not have these bases I comma j. I do not have these bases, let's suppose. Okay, so I have some other bases, some other vectors v2 and let's suppose v2 dash. These are the two vectors that I have. Okay, so if I put any variable, let's suppose we have a equation a and then variable b here, and I'll get to some vector. So anyway, I can form a combination of these two vectors. I'll write the combination of these two vectors to get to some vector. Let's suppose v2 double dash. So what is why am I calling it linear combination? Because here the equations are linear and I'm adding some constant and combining these things together. So this is what I call as linear combination. So it basically refers to summation of a vectors multiplied by scalars. Okay, we basically scale the vectors up. So if you have a vector v1, you'll first scale this vector up. You'll scale this by a constant a, and this is basically a vector multiplied by scalar. Then I have a vector v2. Okay, if I scale this vector by let's suppose b, this is again the scaled version of v2 vector, and if I add them together, and I'll get some vector, let's suppose v3. So this is what I call as a linear combination of vectors. So and I can do it for multiple vectors as well. So in short, I can, if I have vectors v1 to vn, I can write summation of, okay, some coefficients, let's call it ai, and I have the vectors vi, I goes from 1 to n, is equal to some vector, let's suppose capital V. Okay, so this vector capital V is a linear combination of vectors v1, v2, v3, and so on till vn. This is what I mean by linear combination. Take each the vector, scale it, and then add the vectors together. This will give me a linear combination. Okay, these are the vectors and these are scalars. So in together, this is called as a linear combination. Is it clear? Is the concept linear combination clear?
Yes, sir.
Nice. So now let me ask you a question on this linear combination, so that let's suppose I have this vector 1 comma 0. Okay, then I have this vector 0 comma 1. I have let's suppose a and b. So you know that we can get some 2D vectors in this. For example, in this 2D plane, I can go to some vector 3 comma 4. I'll put 3 over here and 4 over here to get these vectors. Can you tell me, if I have all the linear combinations, if I have all the linear combination, all the linear combinations, so which vectors would I able to get? Can I get all the vectors that are in 2D? So by using this 1 comma 0, this basically I hat and j hat. And if I use all the linear combination, I can put any values for a and b. So what vectors can I get by using all the combinations? Can I get all the vectors in 2D? So what do you say? Can I get all the vectors by using the combination of these two? Rian, what do you say?
Yes, sir.
Zubair, are you with Rian? Can you get all the vectors?
Sir, all the vectors that are in a
They're in
plane
2D
like
basically. Huh? I'm
x,
speaking
x,
about
y,
2D,
z.
yes. So Zubair, can we get to all the vectors in 2D by using this I hat and j hat? Yes. So this basically is called a span of vectors. So now we introduced what is called as a span of vectors. So for span, we must have vectors. Let's suppose we have vectors v1, we have vectors v2, and we want to see which vectors are basically reachable and what vectors can we form by using the linear combination of these two vectors. So we have av1 plus bv2. So whatever vectors are reachable by the combination of v1 and v2, we call it a span of vectors. There's a basic definition. What is a span of vector? Span basically means all the possible linear combination when taken, and they can form these vectors together. Okay. So if I write the definition, what is the definition? So given a set of vectors v1, v2, and maybe vn, howsoever vectors are, and all the linear combinations possible, they are called the span of vectors. Okay. So usually if I take a vector, let's suppose we have vectors 0, 1 and 1, 2. Okay. So we have a and b here. Rian, can you say that these two vectors v1 and v2, what's the span of these two vectors? Is it the whole space in 2D, or all the vectors possible? Can we create all the vectors possible in 2D by using these two vectors 0, 1 and 1, 2?
No, sir.
Why can't we? Give me an example by which we can't.
Sir, I mean these are actually the same space. Like these are just 2 points in different.
So they are 2 points, but what I mean by I'm using a combination of these two things. Can we create any vector? So can we create any vector by using? I think we can create any vector. Why I'm saying this? For let's give me a random vector. Let's suppose you are giving me 3, 4, and basically I can multiply. I have to find the values of a and b to get to these 3 to 4. I think it is doable.
So, sir, if we want to like make the value of x plane bigger, then how can we do it?
What I want, can you again come up with the question that you said?
Sir, how can we like make the value of x bigger than y? X is always smaller than y in
X
both
is
examples. X is always smaller than y in both of the examples. So
in both
how
the
can we do
examples.
that?
X is always no. You can make x bigger than y. Just for example, put a is equal to 100, and let's suppose b is equal to 2. Here we have y is now here y is so if you put a is equal to 100 and b is equal to 2, so we'll get 100, and then if we add these 1 plus 4, so we'll get 100 comma 5. So here x is greater than y. Are you able to see it?
Yes, sir.
So don't you think that we can create any number out of this? So because this 0, and we can sort of manipulate these two vectors so as to get to any vector in 2D. Just convince yourself of this, that these two vectors basically, by using these two vectors, I can create any vector that lies in 2D. You can think these two vectors as 2 points as well. It's not necessary you think them as vectors. So let's suppose I'll think them as points. So I'll be able to create any point on this plane, this 2D plane. Okay, for now, just think about the span. Span basically means all the possible linear combinations that we can get out of these vectors if we have these vectors. So here I am claiming that these two vectors are also possible by using linear combination. We can get to all the vectors that are in 3D space, that are in 2D space. So
Sir, I
then
want to like create a vector that has the value of y is equal to 0 and have a positive value of x.
have
I
a
don't
positive
think
value
this.
of x. Y is equal to 0
Yes.
and positive value of x. So you can also do
Yes.
that. So how to do that? Mm, let's just erase it so that I can see it clearly. Okay. So y should be 0. Y over here is this, and what I can do is I can just put negative values. So I'll make this value something and negate this value so that these two cancel each other. Okay, I can solve this equation, but I don't want to solve that for you. But I'm just giving intuition what I can do it.
Yes, sir. Sir, then maybe it is possible.
It is possible. So you can put any a and b. Okay.
Okay, sir.
So are you convinced now these two vectors basically can span all the 2D? So that's why it's called span. Span basically means where is the
Yes,
reach.
sir.
Okay. This is the span. What I mean by span, span is again if we have a set of vectors v1, v2, v3, any number of vectors. So if we take all the possible linear combinations, these a's can be negative and positive as well. So what are the vectors that are possible by giving all linear combination? Basically, is meaning the, is called the span of vectors. From there, we get a concept called as linear dependence or linear independence. So that I'll clear now. Now you some are convinced that we can get a vector, we can get any vector in these two. And what are the possible ways in which we cannot get some vectors? So the question is, what are the vectors only in 2D? We are now speaking in 2D. What are the vectors v1 and v2 in 2D by which I cannot reach all the vectors in 2D? All the vectors in 2D. So let me give you an example. What are these vectors? So first vector, let's suppose I'll write 1 comma 2. Okay, then I'll write, let's suppose 2 comma 4. I'll write this vector is v1 and this vector is v2. So here you cannot reach all the vectors. Why can't you reach all the vectors? Because this vector basically 1 comma 2 is over here. Let's suppose 1 comma 2 is over here. Then this 2 comma 4 is basically scaled version of this, is twice this bigger. So you are some sort of trapped on this line. So you can just find the vectors which are on this line only. So you cannot reach this vector. There is no possible, because for that you must add a component in some certain way to get the access to this vector. So this v1 and v2 vectors by which you are trapped in the line, or otherwise you can again get trapped by this is the first example in which one vector is some sort of multiplication of other vector. Okay, then there is other vector. For example, if we have the vectors n as 0 comma 0 and other vector is also, let's suppose, 0 comma 0. So here we're also trapped on this origin. So you cannot move out of the origin, irrespective of what a's and b's you put. So you will again always land at this 0 comma 0. So in two situations we are sort of trapped. So if we are at origin, we have vectors, we sort of give only access to the origin. And then if we have vectors in which one vector is the multiply of other vector, and we can get this vector from this vector. So we are trapped in that way on a line only. Okay. So the first case is called as linear dependence. So if we have vectors in which there is a dependency. So I have this vector 1, 2, I have this vector 2, 4. So this is v1 and this is v2. This v2 basically can be represented by twice v1. So we call these vectors as linearly dependent. So they are linearly dependent. So what is the meaning of linear dependence? It basically, if we have vectors v1 comma v2 up till vn, and let's suppose some vectors, let's suppose a vector is v, or maybe in this set we have this vector, we can take this vector v2, and if this can be represented, if this vector v2 can be represented by other vectors, so we call this set as a linearly dependent set. Okay, because one vector can be written as a combination of other vectors. So in the example that I gave previously, we had vectors v1 and v2, and here we were able to write v2 by using a combination of v1. And let's suppose we have a vector 1, 2, then I have another vector 3, 4. Let's suppose I have another vector 4, 6. These are three vectors. This is v1, this is v2, and this is v3. If you see that this v3 can be written in a combination of v1 and v2, I can write 1 times 1, 2 and plus 1 times v2, 3, 4. It basically gives me the vector 4, 6, 4, 6. So I wrote a linear combination of v1 plus v2 basically gave me v3. So this v1, v2, v3, I'll call them the linearly dependent vectors, because I can get one of the vector by using the combination of other two vectors. Again, to give you some example, let's suppose I have a vector 0, 4, I have another vector 1, 2. Let's suppose I have some other vector 2, 1, and let's suppose I have some other vector 5, and I have some other vector 8. This is v1, this is v2, this is v3, and this is v4. If you see this v4, I can write it like this. I can say 1 times v1, 1 multiplied by v1, 1 times of v1 plus 1 times of v2 plus 2 times of v3. This will give me v4. Okay, I am taking 1 time of this vector, 1 time of this vector, and 2 times this vector. So this basically is 4 plus 1 plus 0 is 5. So that's here, it checks out. Then we have 2 plus 2 is 4, 4 plus 4 is 8, it checks out. So here v4 can be represented by using the combination of these three vectors. So I'll call this set of vectors as linearly dependent vectors. So they are linearly dependent, because one of the vectors or some vectors can be represented by the linear combination of other vectors. Is the concept of linear dependence clear?
Yes, sir.
Salim, Is it clear? Okay.
Yes, sir.
This is called as linear dependence. So we have here these vectors are linearly dependent. So in the case where we had these vectors which were linearly independent, so in that vector, for example, this 1 0 and 0 1, this v1 and v2, so you cannot form any combination of v1 by which you can get v2. So these two vectors are called as linearly independent. Okay, we started with the basis, we saw them basis, and then we saw what is linear independence, and now I am showing you what is linear independence. If we have vectors, bunch of vectors v1, v2 and v3, okay, so what I can write is, if you cannot represent basically any vector, let's suppose we take this v2, you cannot represent this v2 by using the combination of v1 and v2. You can represent this v3 by using the combination of v1 and v2 and v3, v2 and v1, and you cannot represent this v1 by using v2 and v3. Basically it means you cannot describe any of these vectors by using any other combination of these vectors. So that is the meaning of the linearly independent vectors. Okay, mathematically basically how we write them, av1 plus, let's suppose we'll write x1, xv1 plus xv2 plus and so on, let's suppose x and vn is equal to 0. This is only 0 if all x's are 0. If this condition is satisfied, then we call the vectors as linearly independent vectors. That it basically means if you take any of this vector, you cannot form that vector by the linear combination of other vectors that are in the set. So we had n vectors v1 to vn. So what I'm saying is, if all these coefficients are 0, then only can be this equation can be 0. Otherwise this equation will not be equal to 0. So this is the concept of linear independence. Okay, independence, again to reiterate it, it means if you have a bunch of vectors in which no vector can be represented by the combination of other vectors, that is called the linear independence. So if we now have two vectors which are linearly independent in R2 plane, we call it R2 because the real numbers are there and we have this two numbers. So this is in R2 vector. And if we have another vector 3 4, clearly you can see that these two vectors basically are linearly independent, because this v1 and v2, you cannot get v1 from v2, you cannot get v2 from v1. Okay, so these two vectors, if you form any possible linear combination of these, you can get the access to basically 2D plane. You can get any vector from these two things, or that we call a span. The span of these two linearly independent vectors is called as the span of is basically R2. This is the span of these two vectors. Okay, is it clear? Is the concept of basis, is the concept of span and linear independence dependence clear? Linear combination, is it clear? I cannot see the screen. Can somebody speak?
Yes, sir.
Nice. So from this, I'll go to the concept of basis now. So basis is a set of vectors. Okay, it is a set of vectors. Okay, let's suppose we'll talk in 2D. So it's a set of vectors, basically a minimal set of vectors. So in which number of elements are minimal, which spans the whole space, which spans the whole vector space, the whole vector space. So here, if you see this 1 comma 0 and 0 1, these were two vectors v1 and v2. So they basically can span whole of this 2D space. So these are called basis, standard basis. Why they call standard? Because they have this ones and zeros and it's a norm. It's like some sort of custom to write these things. So we call them standard basis. We can write vectors 2 3 and 4 5 and 6 7. If these are three vectors, v1 v2 and v3. For sure you can just take this vector and this vector, let's suppose, and you can get this vector out of this. v3 can be generated by v1 and v2. So we won't call this basis, because here we have first the dependence of the vectors. So two vectors in 2D space are enough to basically span all the space. You can just take v1 and v2. They'll also be called as basis of R2, because if you see this v1 and v2, here they don't have dependency, and from these two we are able to reach any vector in 2D space, and we call these as bases. The basis basically, it's a minimal set. It's a minimal set of independent vectors. Set of vectors. So basically they should be independent as well. Set of independent vectors. Right? Set of independent vectors. And it should be minimal. The base has three properties. First, it should be a minimal set. Then they should be independent. Okay. Then they should span the whole vector space. So we call that a basis. So a set of vectors is called a basis of vectors if all the vectors in that it's an independent set, and it contains minimum number of elements, and it spans the whole vector space. Is it clear? Is the concept of span clear?
Yes, sir.
Yes, sir.
Now I would like to show you some vectors. I can sort of prove that the vectors, if you take them at random and they have the span of, they can span 2D. So this is the example. So I took a vector over here. Vector v1 is 1 0, and vector, this is a standard basis. Okay. Now what I do is I'll compute linear combination of vectors. Now if I print this, you can see it spans whole of this 2D. Let's suppose at random I'll create some vectors. Let's suppose we have a vector over here 3 comma 4. Okay, then I have a vector, let's suppose 6 comma 7 over here. If I have these two vectors, if I again find the span of these two by taking all the linear combinations, this again spans the whole vectors. So this v1 and v2 are the vectors in which we have, this v1 is the blue vector and red vector. But where I told you they will get trapped if we have this dependent sort of vector. So we have 3 comma 4, and if we have 6 comma 8. So now you know that the second vector, we can multiply this v1 by 2 and we can get second vector. Now you can see that the span is some sort of confined to just one line. So here it's not printed, it printed the span, but it should not get printed. There is a problem in the code, but I hope that you got the concept. So basically what should happen in this case, I'll have to fix the problem in the code, whatever it is. So I basically mean that we have a vector, we had this 2D space like this. So if we had a vector, one like vector this, and other vector was the scaled version of this vector. So we can only get the span as these lines. So it will get trapped over here, because anytime we have v1 and then we have some constant, let's suppose a multiplied by this v1. So you can only get the combination of v1s and you will get trapped on this line. Okay, and you will get trapped in the case of 0 0 as well if you have the vectors as 0 0. Okay, and other vectors, if you are taking the vectors at random, there is a high probability that these two vectors can span whole the 2D space. Is it clear in 2D so far? What is the span? So we discussed, still we have some time, yes we have. So what we discussed some important concepts that I'd like to go through again. I'd like to just sort of summarize these things so that when we move forward, you don't have any problems in understanding that. First, we saw algebra is basically used to solve equations. So what is the meaning of solution of equations? If you have a bunch of solutions and bunch of unknowns, we're trying to find that solution. So here we saw, the first thing is we saw a row picture. So how to compute the things based on row picture. Then we saw a column picture of equations. Okay, this is the first, like before we started with the interpretations and things, unit vectors, we saw these things. And then after we moved on to what we mentioned as, I'll just see if I have written it somewhere. So we, before this even, we saw the addition of vectors, and then we saw multiplication by a scalar, multiplication of vector by scalar, multiplication by scalars. Okay, then we saw how to solve this equation. That this is the fundamental problem that the algebra basically deals with. Then what we saw is, okay, row picture, column picture, yes we saw that. And then we start with the linear combinations. Okay, then we saw what linear combinations are, okay. After that, we saw the definition of what is a span. Okay, what span means. Then we saw what is the meaning of linearly dependent and linearly independent. Linear dependence, we'll call it linear dependence. And by merging these three concepts, we sort of arrived at a concept known as basis. Okay, this is the picture so far that we have went through, and we saw the span as well, and we saw by the combination of these things we get to see the span. Is it clear? Is the thing still here clear? If it is clear, then only can we move. These are the basics of algebra. Now we'll move to the matrix multiplication, transformation, and things like that. If this is clear, then only can I move ahead. Salim, is it clear? I don't want
Yes,
to.
sir.
I don't expect from you that you will understand 100% of the things, but I hope that you will sort of revise these things to get 100% out of it. But you must know all the concepts before I move ahead. Can you just mute yourself? Yes. Rian, can we move ahead?
Yes, sir.
Nice. Okay. Let's now go to the concept of linear transformations. This is a really important concept. If somebody tells me what is the one most important thing that I should understand in algebra, I'll tell this: transformations. Understand these transformations, you are done with algebra at least. Like, you will be able to understand the complex concept that algebra provides, given that you have understood the basics of algebra. Now, what is a linear transformation? Why do we call it transformation? Why do we call it linear? Let's go to that. It basically, if we see it mathematically, it basically is a function in which we give some vectors and it will output some other vector. Let's suppose we have a vector 1 comma 2. So if you some sort of give this to a function and it will spit out some vector, let's suppose 8 comma 12. So we transform this vector into this vector, so we call it a linear transformation. Okay, we'll see why is it not called a function, why is it called linear, and we'll see all of this stuff. But in order to understand the basics, the only thing that I want you to remember at this point is that if we have a vector and you are some sort of transforming this by using a process, we call it a linear transformation. Okay, I also like to show you some visualizations which are taken from Grant Anderson. He has made a really good series of essence of algebra. I took some because it's difficult to visualize. Without visualization, it's difficult to understand the concept of linear transformations if you do not have visual tools. So I'll just show you some visualizations while we go ahead in this. The first thing that I want you to understand is this: that linear transformation basically is like a function which takes some vector and it spits out some other vector. So in order, if I want to write it mathematically, I can just write the transformation which takes a vector and it spits out some other vector. So this is what I mean by linear transformation. Okay, and it has properties what I call as preservation of addition and preservation of scalar multiplication. So we'll see that what is the meaning basically is linearity and transformation 0. We'll see that. So but if you have this sort of ingrained in your mind, we can go to the some video and I'll like to show you some things of the projections. So here I'll just play this. So this is how basically transformation will happen. So I'll just play the video and I'll see how transformations are happening in here. Oh, this is what I mean. If you have a function and you spit out some vector, let's suppose this vector is 5 comma 7 and it'll spit out some other vector, and that's what I mean by the linear transformation. So you give an input vector and then it'll spit out some output vector. That's the meaning of the transformation. Okay, we'll see all of this stuff. And now basically what here is, if we have this input vector and if we apply some transformation, some function onto this input vector, if it is it visible on the screen? Is visible on the screen? Nice. I want to show you the animative and then I'll go back to here. So but I will see, yes, it is visible. So if we have an input vector like this and you are sort of applying some function so that it goes to this output vector, this over here, so we'll call it a transformation. Okay, let's suppose we have a bunch of all the vectors over here. So if we apply some transformation at once in all the vectors, so what will happen is we'll some sort of twist this space like this. It is some sort of transform all the vectors at once. Okay, so this is the meaning of transformation over here. So you have a vector, and if you apply some function, or if you do some transformation, it will just take the input vector and convert it into the output vector. It will basically transform whole the space in 2D. If you see this 2D, so in here we had this vector. So this was our this was the vector this was the 2D space in which we had all these vectors, and then when we applied the transformation, it somehow stretched the space. It changed all the vectors at once. If you see it over here. That's what I mean by a transformation. Like visually, this is the meaning of the transformation, what a transformation basically means. Okay, now we want to see what is so special about this transformation. So here you can see if we represent this 2D plane by the grid of points in here. So if we apply some transformation, what will happen? So you will see that over here. This will happen. So basically, all these points will get transformed. So the transformation you saw, if you see again, so we had originally a bunch of points. So bunch of points, basically all the points that are in 2D plane, and then we applied a transformation. All these points basically got moved. This space somehow got twisted. If you see it, this space got twisted like this. This is what I mean by transformation visually. Now I would like to see what are the properties of this transformation. There are only two properties in this transformation. Okay, the first thing is this origin should remain intact. This origin, the origin that we have, it should remain. Whenever you are transforming the plane, if you have that plane, if you are transforming, this origin should remain fixed. You cannot move this basically that's why it's called the property of linearity. I won't divide into the mathematical details, but here I want to make you visually understand this. The first thing that I want you to understand is that while applying a transformation onto this 2D space, or on any space for that matter, the origin should get fixed. The origin should not move. This thing should get fixed. And the second thing is that these lines should be evenly spaced. If you see, this is for example, this is our plane. The first property that I want is this origin should get fixed. Okay, and then if you saw this transformation, the origin was fixed over here, and you saw in here these lines were evenly spaced. All these lines are evenly spaced. There is no uneven space. So if you take an example like this, this is not a linear transformation, because the origin got shifted and these lines basically intermingle, and there is this basically is not linear transformation. So what are the two properties of linear transformation? Like speaking visually, the origin should remain intact. The origin should not move here and there. And the second property is that the lines that we had in that, if you see the grid of lines, these should be evenly spaced, equally spaced. Okay, this is not linear transformation. Again, if you have this is again not, because origin moved here. So you saw that origin moved. This is not a linear transformation. If you see it over here, this is again not a linear transformation, because this is not evenly spaced. Okay, so can you see this line? Why is it not linear transformation? If you see this, so what it does to this line, so it will sort of curve it, it will bend it. So you saw that these points got basically changed. So there are only two things: origin should get fixed, and the other thing is these lines should be evenly separated. So this is again not a linear transform, because this diagonal line basically gets curved. These grid lines remain parallel and evenly spaced. They should remain parallel and evenly spaced, and then origin should be intact. All these things are linear transformations. Whatever now you are seeing on screen, these are all linear transformations. Okay, transformation basically is what this is the input vector, and there is something happening to the space, and it is taking vector to some other place, and we want to find this place, and we want to find what is the mathematical meaning of this transformation now. And now if it is visually clear, then only I can move towards my tab screen, and I can show you how these transformation can we now show mathematically. Is it visually clear? What is the meaning of
Yes, sir.
transformations? Basically, we somehow work with the
Yes, sir.
space somehow. So we have a space, and we do something to the space. We can rotate space. We can some sort of stretch the space. But the only two properties that should be there visually: origin should be fixed, and the other property is that the lines should remain parallel and equally spaced. These are the two things that you want to. Now I want to some sort of show this thing visually. So if I have a vector, let's suppose x input vector, or x1 and y1, let's suppose x2, I'll do some transformation to this vector. So then I'll get an output vector which should be, let's suppose, x out and y x2 out. So I want to find this transformation mathematically. So this is here the transformation part. Okay, so this is the transformation part that I want to basically show you guys mathematically. So how to basically now deal this mathematically, that we'll see now. Okay, so now let's take an example. I'll again move to the screen so that I'll show it visually. Let's suppose we have this vector -1, 2. This is the vector. Okay, this -1, 2. This is the vector. So it can be represented. This vector can be represented by minus I cap, because this is our basis, minus I cap, and then plus 2j cap. So because this is how we visually represent this vector. This is the vector which I represent this. This basically means if you want to reach this vector, go in the negative direction 1 unit, and in this j axis, or this j hat, go 2 units. So you will reach this vector. So this is the meaning of this visually. So now we'll apply some transformation onto it. You applied some transformation. If you again just see it, you're applying some transformation. Okay, nice. So we have now this transformed I. So all the vectors in the space got transformed. So here we have this transformed I, we have this transformed j, and we have this transformed vector v. Okay, so we did some transformation. Now whatever the transformation that we did, we want to see it mathematically, and we want to show it mathematically. Okay, so here you saw that all these vectors got some sort of transformed in a certain direction. So now if you want to find the value of this transformed I, transformed j, and the resultant vector, So what I can mathematically see is that this transformed v, whatever this transformed vector got, it basically is the same linear combination of transformed vector of I and j. Initially, if you see what this v was, if you saw this v, this v was some combination a of I cap plus b of j cap, and here in this particular case, this was -1 of I cap and 2 times of j cap. This was our v initially. So we some sort of applied some transformation which we want to mathematically capture. And then what we did is, I'm saying this v transformed vt is equal, the coefficients will remain the same, -1 it will be the same, but this I got transformed. So I'll write transformed I over here, transformed I plus this 2 will remain the same, this coefficient will remain the same, but instead of this j I'll write transformed j, transformed j. So now I learned how to basically get this output vector. Still I have to mathematically model this transformation. So if anybody says me, okay, how to mathematically get the vector if you have a v vector and you have some transformation t and you are getting some v2 vector out of this, so how to basically you can say this, I'll say I'll just represent this v1 into the basis vector, into some vectors which I call bases, because this v1 can be represent the base. I'll say, let's suppose I cap a plus b j cap is the vector v1. Okay, now I'll apply this transformation t to this v1 and I'll get this v2. How I can represent this v2 basically is, I can say this transformation change this vector I, this transformation change this vector j. I can write t transformed of I cap plus b transformed of j cap, and I can represent this. This is equal to v2, the transformed vector. So the first thing that we have to mathematically model was, how can we model this output mathematically. So now we reached how to basically get this. Now we want to model this transformation. Is it clear that is it clear that till this point? So how I got to this v2, how I got to the output vector?
Yes, sir.
Nice. So after that, again to show you the visualizations. So now I'll just find the transformed I, where this landed, where this transformed I landed, and I'll see where this transformed j landed, and I'll just put the values in this equation that I found. So if you see in here, transformed I basically landed at 1 minus 2, and transformed j landed at 3 comma 0. I'll just put the values over here. The transformed v that we have, so I'll say transformed I, this basically landed at 1 minus 2, and transformed j, it landed at 3 comma 0. So I'll just switch the screen to show. So here our vector initially was vector v1, and we applied some transformation and we got to vector v2. So in order to get this, compute this v2, what I told you is, you have to first represent this v1 as a linear combination of the basis vectors that we had. So in here, this v1 was represented as -1 I cap plus 2 j cap. Okay, in order to apply this transform, after this v2 can be represented -1, not sorry, -1 transformed of I plus 2 transformed of j cap. Okay, now I know these are the values of transformations. So in order to get this v2, what I can write is, I can write v2 is equal -1 multiplied by 1 minus 2 plus 2 multiplied by tj. Tj is 3 comma 0. So I can get -1 plus 2 plus 6 0. So this will be equivalent to 5 and 2. So here is the transformer vector. So we took this vector, which was as, the vector was basically this vector -1 and 2. So -1 and 2, this vector basically got transformed to 5 2 by using the transformation that I just showed you. Is the concept of transformation so far clear, how we sort of got these transformed values? So the only thing that I have to keep the track of is where these basis vectors went. So if I have the track where these basis vectors went, now what I can do is, I can just keep the track of these basis vectors and feed any vector to this and see where will it land. So this is a very important point. I need to keep track of the basis vectors, basis vectors. So if I apply some transformation, okay, I applied some transformation, so that transformation will happen to these basis vectors. The thing is, if I want to capture that transformation for any vector, so what I can do is, because I know that any vector can be represented by using these basis vectors. That's the definition of basis. Basis basically means we can get to any vector by using some linear combination of the basis vectors. So if I apply some transformation, the only point that I need to take care of is that where these basis vectors land. If I know that, now I know that if I have a vector, let's suppose v, I have the basis vector v1 and v2. So if this v is represented as a times v1 plus b times v2, if I applied some transformation, so I'll just keep a track of where this v1 and v2 went, where this basis vector went. Let's suppose they went to tv1 and tv2. So I know that this vector v will get transformed to some v dash, and the answer will be a times the same coefficient and the transformed v1 plus b and the transformed v2. Coefficients won't change. I need to just keep the track of these basis vectors. Is the transformation clear? Now I will capture this transformation mathematically. Is it clear so far?
Sir.
Yes, sir.
Nice. So again, going back to the visual format, so I can show you how I can compute different things now. So this is the visual thing that I was showing you. So here I just wrote the combination -1 of 1 minus 2 plus 3. So that's where it landed. So this is how I can get the values 5 comma 2, and here the 5 comma 2 value is for this transformed v that is shown in the blue over here. Okay. If there, nice. So I don't think I have other animations to show you, but I can just continue the discussion over here. Now I want to capture the transformation. So what I can do is I can write this tv1, the transformation. Let's suppose this basis vector, the vector I cap, it went to, let's suppose x1, x2. Let's suppose this v2 vector, it went to some y1 and y2. Okay. So this is what happened to the basis vectors after transformation. So initially basis vectors were, let's suppose, v1 and v2. This was the vector v. Let's suppose this was one basis vector. We had w. It was w1 and w2. These were two basis vectors. Now we know by definition the basis vector, any vector can be written in some linear combination of these two vectors. Okay. So what I'm saying, I applied some transformation. I told you that you don't have to worry about what happened to other vectors. Just think what happened to these two vectors. So I can write t of v and t of w. Let's suppose this t of v, what happened to it was x1 and x2. It landed at x1 and x2. And this w vector, it landed at y1 and y2 after transformation. Okay, so this is what happened to the vectors. I can sort of collect these two in a matrix like this. I can write x1 and x2 and y1 and y2. So this is where the first basis went, transformation of vector. Let's suppose we call that vector v1 or basis b1, and this was vector v and w. So these were the bases of my basis vector after transformation. Okay, so if I have a generic vector now a comma b, I have a generic vector ab. I want to see where it landed. So if you see what happened, so we had this again to reiterate. Let's suppose we have a vector v which was ab. We applied some transformation over to this, and this vector got changed over to vt. Vt means transformed vector. Okay, we want to see what happened to this. So what I told you that we can write this ab in terms of basis vectors. Let's suppose we have the basis vectors, and v and w are the two basis vectors. So I can write this a times v. So this vector ab can be represented, let's suppose, by using x1 of v plus, or maybe in the standard basis I can write a times 1 0 plus b times 0 1, some things like that, and these can be generic vectors as well. Okay, so in here I can write a v1 or av plus bw. These are the two basis vectors that I showed, and these are the coefficients of these vectors. Okay, so this is the form of vector v which I wrote in the bilinear combination of its basis vectors. Is it clear so far? Let's call this vector, I'll call it, let's suppose v dash. V dash is the vector. So what I am doing is I have a vector v dash which has values a comma b, and I apply a transformation vt onto this. So what I am saying is I have basis vectors v and w. So I can represent this vector v dash into these two basis vectors as av plus bw. So because these v and w are basis of this vector space, so this v dash basically is equal to av plus bw. Now I want to see what is the value of this vt. So what I am saying is I'll say a transformation of this v plus b transformation of this w. Okay, keep this in mind, this thing in mind. So I am capturing this, basically this thing, into a matrix. So I am writing a matrix in which the first column is transformation of V and the second column is transformation of W. Okay, now I'll write this A and B in a succinct way like this. Okay, so A TV plus B TW is basically written like this. Okay, so in our specific example, we had these numbers, let's suppose basis vectors after transformation, got A and B and C, not A and B, sorry. So we wrote the transform x1 and x2 and v1 and v2, y1 and y2. So this vector was basically equal to x1 and x2, and this transform vector got equal to y1 and y2. Okay, then we had this A and we had this B. So if we expand this portion, so I'll write ax1, okay, plus by1, and then ax2 plus by2 plus this. So what I did is I wrote it like this. This was x1, x2, y1 and y2. So here we had A and B. Okay, this is what I mean by matrix multiplication. This is matrix multiplication. We memorized nothing. If you got this intuition, now you know why matrix multiplication is done in a certain way. So what we do, we took this A and multiplied the whole of this column. We took this B and multiplied the whole of this column. If you know the old school way, so how we did it, x1, x2, y1, y2 multiplied by, let's suppose we have to multiply matrices. So what we'll do is, we'll take this, multiply this, take this, multiply with this. So we'll take this, multiply with this. So this will be ax1 plus, we'll take this, multiply with this. So this will be by1. Again, and now we'll take this, multiply with this. So ax2. Then we'll take this, multiply with this. This is basically going here, then here. So a2 plus by2. So do you think that we got the same results over here? So how many of you got intuitively clear how this matrix multiplication was defined this way it was defined? So that's the reason. Again, just I'll summarize the topic, because I told you this transformation is really important and we'll go into the matrix multiplication in detail, but I want you to understand how these things are done. So we had some vector V and it was transformed into some vector Vt by using some transformation T. So what I told you that in order to see what this transformation is, I'll capture this transformation into a matrix, and I'll only capture this Vt by using what is called as basis. So this V can be represented by using, let's suppose we have V1 and V2 are bases. So this is AV1 plus BV2. Okay, so this is represent, this V1 and V2 are basis vectors. Now what I told you that I just need to keep track of where these basis vectors went. So I'll write A where this basis vectors went after transformation, and I'll write B where this transformation, what happened to this V2, and I'll get V transformed. Okay, now what I told you is that I can capture these T1 and V2 in a matrix. So I can write a matrix TV1 TV2. Okay, and I can write any generic vector, this A and B over here. This is what I mean by matrix multiplication. Here we will have a bunch of numbers over here, Again, if I have a matrix like this, x1, x2, x3, x4, and then a lot of values over here, a lot of columns like this, then you know that this basically is a transformation. This matrix represents basically a transformation. Okay, so this is where the first dimension landed, where the first basis vector landed. This is where the second vector landed. This is where the third vector landed, fourth vector landed after transformation. This is where the fifth vector landed. If I want to get anything, I'll just write A, B, C until how many, so our values we have here. Now we got the value that if we have to multiply two matrices, you know that if we have a matrix M cross N and we have a matrix P cross Q, this is the other matrix. So now these N and Q should be equal. Then only we can multiply these matrices. If you understood this point, then now you know the reason why should be these two equal. Otherwise we cannot multiply. Basically we are taking this A multiplied with one column. We are taking this B multiplying with other column. We are taking this C. That's why the rows of this should be equal to columns of this. Then only can we say the matrix multiplication is compatible. Otherwise it won't happen. Because the definition of matrix, how we got the matrix multiplication over here. Okay, so how many of you are now confident that you understand that why is this matrix multiplication done in a certain way? Rian, are you clear with this?
Yes, sir.
Okay, nice. I think our time is over because I needed to sort of again go into the different types of matrix multiply. How can we perform these, and we'll take that in next session. If you have questions, I'll just wait here for some seconds to take questions. Otherwise, I'll stop recording. Do you have questions? Nice. I'll just stop recording.